Welcome! In this video, we're going to go over a common proof that the square root of 2 is irrational. I'm going to be assuming that you have some basic proof experience, but I may still explain things deeply at times. If you have any questions, feel free to leave a comment, and I'll try to get to it. So, let's get into it. It turns out that this result is true in a more general case. The square root of any prime number is irrational. Not only that, but the actual proof for the general case is as easy as the proof for the root 2 case. It then makes sense for us to simply prove the general case. If you need a proof for a specific prime, you may simply modify the proof slightly. While we could prove this result from first principles, I've chosen to start with Euclid's lemma. I assume that you know what primes are, the properties of integers, and the definition of divides. If you would like a video on the foundations of number theory such as those, let me know. Euclid's lemma states that if a prime divides a product of two integers, then the prime must divide at least one of the integers. From this, we can trivially prove corollary 1.14.1, which is a less general version of the lemma. It states that if a prime divides a square, then it divides the root. This result will be crucial for our proof. When I cite this in my proof, you could also replace it by citing the fundamental theorem of arithmetic, which states that all integers have a unique prime factorization. But for simplicity's sake, I'll be using this corollary. Now, let's look at the proof. Let p be prime. Then, the square root of p is irrational. We say a number is irrational if it is a real number that is not rational. So, to prove that the square root of p is irrational, we have to show it isn't rational. If you wanted to be very rigorous, you should also show that the square root is a real number, which is true because p is a positive integer. We start by letting p be prime. Then, to show that the square root is not rational, for the sake of a contradiction, we assume it is rational. Our goal is to find a logical contradiction to prove our assumption false. We then invoke what it means for a number to be rational. It means it can be written as a over b. Of course, b cannot be 0, since division by 0 isn't well defined. There is one more caveat, however. A property of rational numbers is that they can always be reduced and still match this form. Thus, a and b must be relatively prime. It means they share no factors except the number 1. For example, with this definition, 2/4 is rational since it equals 1/2, which is rational by our definition. 2/4 is then rational by equality rather than directly. The reductive component of the definition is very useful for simplifying proofs, as you'll see. Now that we have the form of a rational square root p, we can square both sides. Because b isn't 0, we can multiply both sides by b squared. Since the integers are closed under multiplication, b squared is an integer, and we can invoke the definition of divides. It must be the case that p divides a squared. Now, we can invoke our corollary 1.14.1, and we know p must divide a itself. Thus, a is a multiple of p, and we can rewrite it as p times c for some integer c. We can then go back and substitute this into our equation. We end up with p on both sides. Then, because p is non-zero, we can divide both sides by p. Just as before, we have that p divides b squared by the definition of divides, and of course, by our corollary, p divides b. And so we arrive at our contradiction, since p divides both a and b. But we assumed that the only factor to divide both a and b is the number 1. Thus, our assumption is false, and the square root of any prime must be irrational. Directly following from this result, of course, is that the square root of 2 is irrational since 2 is prime. If you want a specific proof for the square root of 2, you can go back and replace the p's in this proof with the number 2. Now, as a bonus, I'd like to also show that the square root of 6 is irrational as well. Similarly, I'll be proving a more general case. To begin, we need a small lemma. We need to show that when two distinct primes divide an integer, the product of those primes also divides the integer. For example, 2 divides 6 and 3 divides 6. Thus, it must be the case that 6 divides 6. We start with our assumptions. and we construct a form for integer c using the definition of divides. Since m is an integer, we know q divides p times n. We can now invoke Euclid's lemma to show that q must divide either p or n. But since q and p are distinct primes, q cannot divide p and must divide n. Now we know that c is q times p times some integer, and thus p times q divides c. Using this lemma, we can construct the following proof. Let's prove that the square root of the product of any two primes that are distinct is irrational. Since 6 is 2 times 3, which are distinct primes, we will be showing that the square root of 6 is irrational as well. The proof starts off very similar to before. We use a contradiction, invoke the definition of rational, and we square both sides. Lastly, we can isolate a squared by multiplying both sides by b squared. The proof becomes different here, because we must point out that both p and q divide a squared, and by our corollary, a itself. By our lemma, since p and q are distinct primes that divide a, the product pq divides a. It's important that we show the product divides a, since it will enable us to isolate b squared on one side. Now we can use the definition of divides to show p divides b squared, and by our corollary, b itself. Thus, a and b are not relatively prime, which is a contradiction. I hope this video has been useful for you. From here, you could show that the square root of the product of 3 distinct primes is irrational, for example, and I encourage you to try it. Then, maybe you could prove it for an arbitrary number of distinct primes, or you could start talking about odd powers of primes or prime factorizations. Anyway, if there's any math-related videos you'd like me to make, or if you have any questions, just let me know. I hope you learned something.